Alright, welcome. So we'll pick up sort of where we left off on, let's see, what was that? Thursday. So we had started chapters 3 and 12. We started talking about linear regression. So this lecture will probably, we'll finish up those notes. It won't be an hour and 50 minutes. So it'll be a little shorter. I'll recap some of this on Thursday, and we'll spend a good amount of time going through some other examples using StatCrunch. So the way that you will do linear regression is through some type of software. We will be using StatCrunch. You can do linear regression with your TI-83s, but I'm not going to show you how to do that. Mainly because it's kind of a pain, and the output you get is weak. There's not a lot there. It just takes a lot more effort to get the things that we need. So what the point of this linear regression stuff is I'll show you how to do it in StatCrunch, but really what you need to be able to do is look at output specifically from StatCrunch and know how to interpret it. So just like we do with the, say, t-test output on the calculator. You need to know what the z is, what the p is, etc., and how to interpret it. So that's what we'll be doing here. So say on an exam, like maybe exam 3, I will give you StatCrunch output. I won't, there may be a take-home portion, I haven't decided that part yet, but you probably won't be doing your own regression. At least not a lot of them. So just trying to get you to understand the output. So we're working through this example where we're buying a used Toyota Corolla. We looked at the data last time and we noticed, yeah, there seems to be some type of association here. There's some type of pattern. And if it's a linear form, then we can use this tool, simple linear regression, to fill in data gaps, make predictions, do all kinds of cool stuff. So on Thursday, we went through the univariate exploratory data analyses. So we were looking at each variable one by one. Our response is the price. That's what we're interested in, how it changes. And we're going to see what effect age has on the advertised price. So we expect that there's a negative association. So as these cars get older, they tend to cost less or have a smaller or less advertised price. Now note that both of these are quantitative continuous. That's what we're going to require right now for linear regression. However, that's not a necessary requirement. So you can do regression if you have one or both discrete variables. You can do regressions with categorical variables. But we won't get into those, so if those are things you need to know, take some more stats classes. We looked at the 5-number summary of each variable. So age, there's the explanatory variable. And what we noted was we need to pay particular attention to the values of the explanatory variable that we have. So in this case, our minimum is 1. So the newest car we have is 1 year old, and the oldest is 13. That range from 1 to 13 is called the scope of the data. So we'll talk more about this shortly, but this is where the data live. This is where we have information. So what this means is, within this range, this is where our linear regression will make sense. We can use the tool there. You can, but you shouldn't try to learn about cars that are newer than 1 or older than 13. You'll encounter some issues, and we'll talk about those. So we plotted these these variables. They look pretty good. Nothing unusual that we need to correct, so no outliers specifically. And we plotted both of them together with a scatter plot, and now you can visually see that negative association. And what we noticed was we don't have any information for cars that are 2, 9, or 11. So if we wanted to, or 12 for that matter. So if we wanted to, say, buy a 2-year-old used Toyota Corolla, what would you expect to pay? Well, that's what we'll figure out. So our goal is to describe and quantify this linear relationship. So, I think then, yeah. So we describe the association, negative, linear, pretty strong, but we can refine that later once we see a correlation coefficient and no outliers. So this means this is going to be a perfect relationship to examine and investigate using simple linear regression. It's kind of the perfect applicant. So one thing you'll get from StatCrunch, and I'll show you this more on Thursday because I can't really show you the computer aspects on this recording, but we'll do that Thursday. One of the outputs is this scatter plot, but with what's called the fitted line going through it. So this is our goal. We want a straight line, the best straight line that describes these data points. So you can imagine that there are a lot of different straight lines you can draw through these data. Maybe one that looks like that, but maybe that's not the best. So what is the best straight line that we can draw? So the idea is we want a line that's as close as possible to every single data point. So thinking about that a little more mathematically, we want a line such that the distance from any given point to the line, so the vertical distance, is minimized. So this distance here is called a residual. And these 2 points have different coordinates. So this black point, this is an observed data point. This is one of the values from the table on page 1. So this has coordinates x, y. And more specifically, that's going to be an x of 3, because it's a 3-year-old car. And its price, I'm not sure, near $13,000. So if we look at the first page, $12,999. Yeah, so pretty good. Okay, so that's the coordinates of the top point, the observed data point. So this point that's on the line, this is what's known as the predicted data. And we'll define that better shortly. And this has coordinates that are similar, x, but now a y hat. So the hat over the y is sort of like the p hat and the x bar. It's an estimate. It's a statistic. So the x is the same. The y hat, I don't know what it is. we can find that out later. We'll come back to that. But it's going to be something near 11,500, I'd say. Okay. So what we want, again, is a line such that these distances between the observed data and the predicted data are minimized. So if those distances are really small, then that means the line will be close to that point. And we want it to be close to all of the points. So the way that that's done, and this is where we ended on Thursday, is through a method called least squares. So it's kind of like the computation for a standard deviation. Those residuals you can think of as a deviation, so a distance between 2 points. We don't really care if they are positive or negative. So in this case here, because the observed point is above the line, this residual is going to be positive. It will be bigger than 0. Down here, say for this point, this residual will be negative because the observed data point is below the line. So if we just added up all of the residuals and wanted to minimize that total, well, what happens is all of the residuals will add up to 0. I think for pretty much any line you draw through these data points. So trying to keep the total residuals minimized doesn't work because it will always be 0. So what we'll do, like we did with standard deviation, is we'll square these. We don't care if they're above or below. We just want to know how far away from the line are the observed data points. So that's what this process of least squares does. It finds the line that has the least total squared distances from the observed points to the line that's drawn. And the way that that's all done, the technical details require calculus. That's beyond this class. If you've had calculus and you want to talk about it, I'm happy to do that. Otherwise, take some calculus, it's fun, and take some more stats classes. So that's how the best fit line is found. Okay. So what's actually being found is the equation of this best fit line. So as we discussed before, you probably learned that for any straight line, it has the equation of y equals mx plus b. So what we're going to think about are these two terms, m and b, as parameters. So kind of like a mu or kind of like a p, something like that. Once you have these two components, these two parameters, then you can describe this particular line for any value of x. So what we need to know is, for this best fit line that exists, what is its slope, m, and what is its y-intercept, b. So what least squares does is it gives us equations for the slope and equations for the intercept, kind of like statistics. So what we get from StatCrunch is this equation. Y hat equals a plus bx. Hopefully you can see all of this. I'm trying to be zoomed in but not too far. So here's our equation of a straight line. So what's different is, well, a few things. Since we're talking about the best fit line, those are all of the y hats. So this is telling us if we want to know a predicted response, in this case a predicted price, we'll have some intercept, some slope, and some x. So x is your explanatory variable, in this case age. So from your earlier courses, you had something like slope was the m. Now slope is going to be the b, which is kind of unfortunate, since before b was your y-intercept. Now our y-intercept, we're calling it a. So in this equation, there's a. It's all by itself. That's indicative of being the y-intercept. It doesn't have anything else with it. It's a constant, so that's the y-intercept. The b will always be multiplied by your explanatory variable value. That indicates it's the slope. Okay. So a and b, those are numbers, those are statistics, and StatCrunch will do the least squares for us. It will do all that hard work, and it will just tell us what a and b are. So once we know those, then we have the equation for our best fit line, and then we can use it to make predictions, as we'll do shortly. So we can go over what these components are, and I'll go over them kind of briefly so you can read them and think about them. So again, y hat, this is a predicted value of the response. Now, what's maybe a little bit different is that you might expect that the line and points on that line would refer to an individual car. All of the data points and the scatter plot, these are all individual cars. So you might think a point on the line is a predicted price for an individual car. But in fact, that's not what's happening. So what this best fit line is actually doing is going through the average at each of these points. So for each age, it's finding the average. So kind of an odd technical detail to this is if you turn your scatter plot to the side and you pick a particular value of the explanatory variable, say when x is 10, what's being hypothesized is that the population of prices, of advertised prices, for all used Toyota Corollas that are 10 years old follows a normal distribution. And its mean, I drew that kind of bad. The mean is the point on the line. So we have kind of a bunch of these normal distributions at each age. That's why we have variability in these prices. They're coming from a normal distribution. They're all the same normal distribution in terms of the spread. So they all have the same shape. What's changing is the mean. So in this case, the mean starts high, and over the ages, as age goes up, the mean